Question 12 wants us first of all to write an equation for the reaction between manganate 7 and iron 2 plus. You know it's a redox reaction because Fe2 plus is being oxidized to Fe3 plus, manganate's being reduced, it says that in the question. As soon as you know it's a redox reaction, you should think of doing half equations. It doesn't tell you to do that, it may not tell you to do that, but you should think of doing that because that is the way to make sure you get a balanced equation if you do the half equation thing. So for the iron 2 one, of course, it's very easy. We just have Fe2 plus being oxidized goes to Fe3 plus, and obviously it has to lose an electron to balance the charges up. Now manganate 7, you are supposed to know that manganate 7 is MnO4 minus. If you should happen to forget it, you can work it out, because you know that the manganese is plus 7, and you know that ions ending in 8, like sulfate, carbonate, nitrate, all of those, they're called that because they have a bunch of oxygens as well as the element. So manganate, you know, would have a bunch of oxygens as well as the manganese. And you know it has to have a negative charge, because that's what 8 ions are, they're anions. So you think, well, if the manganese is plus 7, we're going to have minus 8 to get it to be negatively charged. So that would be 4 lots of minus 2, which would make it 1 minus overall. So you can work out it's MnO4 minus. So you shouldn't need to do that. You're supposed to know what manganate 7 is. Manganate titrations and iodine titrations are specifically on the syllabus. You're supposed to know the details, including the colour changes, the practical aspects of doing those things. So make sure you revise that. They're not just random examples in your questions. They're things you're supposed to know about. Okay, so let's do the manganate half equation then. So we got MnO4 minus, and it tells us in the question that it goes to Mn2 plus. So you just follow the standard recipe for half equations. You balance, first of all, the elements that aren't hydrogen and oxygen. Well, manganese is already balanced, so that's fine. Then you do the oxygens, and you do that by putting waters in to balance them up. So we've got 4 on the left, so we need 4H2O on the right. Next you balance the hydrogens, and you do that provided it's in acid solution or neutral solution. You do that by putting H plus in, and this says acid solution, so that's fine. 8 hydrogens on the right, so we need 8H plus on the left. So now all of the elements balance, but the charges don't, because we've got 8 plus and 1 minus, so 7 plus on the left, but only 2 plus on the right. So we've got 5 extra positive charges on the left. That means we need 5 negatives on the left to balance it up, and they'll come in the form of 5 electrons. Okay, so it's absolutely standard recipe. If you haven't got that yet, you really must learn to construct half equations like that. Now to combine them, they've got to have equal numbers of electrons but on opposite sides. So they are on opposite sides, but the numbers need tweaking, and it's easy to do. We've just got to get 5 electrons in this top one, and then they'll cancel out with the 5 here. So we can just put 5 there, 5 there, and 5 there. And then if we add it up, we get 5 Fe2 plus MnO4 minus plus 8H plus. We won't put the electrons in because we know those have cancelled out. So that gives you 5 Fe3 plus Mn2 plus 4 waters. Check if anything needs cancelling, but it doesn't in this case. Check the charges add up to the same thing on both sides. So we've got 10 plus and 8 plus is 18 plus and 1 minus, 17 plus on the left. 5 3s are 15 plus 2, 17 plus on the right, so that's reassuring. Okay, so that's our equation. Okay, and the crucial thing about it is that it means that you need 5 Fe2 plus for each MnO4 minus. Okay, so now the next bit is that we have to work out the identity of element X from the titration results. In a titration calculation, you always know where you start. you're always going to be calculating moles is equal to concentration times volume in dm cubed. That's what titrations are for. That you know the concentration of at least one of the solutions, you measure its volume, and so from those two things you can get the moles, which, as you know, is what you always need to get into your calculation. So we can do this for the manganate because it gives us the concentration, which is 0.0250. It also gives us the volume. Obviously, make sure you get the right volume. It's 25 cm cubed of that, 28.8 cm cubed of the manganate. You've got to always double check you've got the volumes the right way around. So times 28.8 divided by 1000, remember, to put it into dm cubed, which is 7.20 times 10 to the minus 4 moles of MnO4 minus. Okay, now again, the next step, you know what to do, which is that you've got the equation, we just worked it out a minute ago, and it told us that for each mole of MnO4 minus you need 5 moles of Fe2 plus. So we can get the moles of Fe2 plus in the titration is 5 times the moles of MnO4 minus. Okay, that just follows from the equation that we worked out a minute ago. So we just multiply that number by 5 and we get 3.60 times 10 to the minus 3 moles of Fe2 plus. Okay, so then we think, right, how do we relate that to the amount of this? And the key is that we dissolved the FeXO4 in 500 cm cubed, but we only used 25 of that in the experiment. So we've got to scale up. And again, 9 times out of 10, this is a step that you go through in a titration calculation. Occasionally, you just titrate the whole sample, but usually you make up a big pot and you just titrate a little bit of it, and you have to scale up. So that's what we're going to do now, which is that the total moles of Fe2 plus in 500 cm cubed of solution, and you just multiply by the big volume over the little one. So it's 500 over 25.0, because that was the volume we used in the titration. That's the total volume, times 3.6 times 10 to the minus 3, which is 0.0720 moles. Okay, so now we know the moles of Fe2 plus, but we're interested in this compound. But you can see from the formula that there's just one Fe2 plus in it. So we can then write that the moles of FeXO4 in 17.81 grams, because all of that was dissolved in the 500 cm cubed, that will equal the moles of Fe2 plus in 500 cm cubed, which is what we've just worked out is 0.072 moles. Okay, so we're just making that connection between the moles in solution, which we've deduced from the titration, and saying that because of the formula just contains one Fe2 plus in it, then that's the same as the moles of that compound. So now we can work out the MR of that compound. Okay, so we get MR is equal to mass over moles, which is 17.81 divided by 0.0720. And that works out to be 247.4. So the last step, which we'll just do over here because we're running out of board space here, is that we can work out what the Fe and the O4 add up to and subtract that from the total to work out what the atomic mass of X is. So we get that FeO4 has MR equal to 55.8 for the iron, plus 4 lots of 16 adds up to 119.8. And that means that the relative atomic mass of X is the difference between that, which is the other elements, and that which is the total. Okay, so it's 247.4 minus 119.8, which comes in at 127.6. So then you just go to your periodic table and you say, right, well, what element has a relative atomic mass of 127.6, or at least which is the closest to that? But in fact you find in this case it works out perfectly, because that's the relative atomic mass of tellurium. That makes sense because we know we're used to SO4, 2 minus sulfate, and tellurium's in the same group, so that's kind of reassuring. So we just say, right, therefore X is equal to tellurium is your answer.